Everybody, welcome to our webinar Discover True Load. And for this occasion, we have the honor to welcome Tim Hunter from Volstar Technology, who will present his product in this Star Wars Day, since it's May the 4th, and as you know, May the 4th be with you. Let's just some usual recall. You know that we are today with some exceptional time for our webinar, since usually we begin at 11:30. But today we will begin at 11 in order to enjoy the presence of Tim Hunter. And thanks to him, because in USA it's 4 a.m. so it's very difficult. So please enjoy the presence, ask the question, because we need your support for this situation. So as you know, this webinar is dedicated to simulation, design, and system engineering, and most usually product presentation, as we will do today. We do it 2 webinars per month at this time, and we suggest strongly you to send us some topics at 3dx@keonis.com. You don't use this solution enough, please do it. We will try to be helpful and to propose you some good solution for that. So what will be today, as you see, introduction to Volstar Technology, which is this company which produces True Load, and presentation of True Load, which is the product which will be in a lot of interest for us. And for that, I will let the talk to Tim Hunter. Tim, hope you're very well, and I pass to you the end. So here, yes, now you should be able to share your screen. Some minutes.
Okay, let me see if it shows.
Yeah, that's okay. It's all right.
Okay, so you can see my screen?
Yeah, it's perfect.
Okay, perfect. Well, thank you very much. It's great to be with you all today, and may the 4th be with you, right? We'll get right into this presentation today. Most of the presentation is going to focus on our flagship product, True Load, and then I'll show in some features of our new product, True LDE. So we'll get in and we'll see all these exciting products here today. So what you see on the screen here is a little project we did with one of the local universities with their SAE Baja car team. And we're here, you can see we've calculated the loads and the suspension on their Baja car. This was a fun project we did, and we'll get into the details of this towards the end of this presentation. So without any further ado, let's get right into this. Wolfstar Technologies, it was founded by me, Tim Hunter, 10 years ago in 2010. I can't believe 10 years has gone by. Prior to that, I was chief engineer at Harley-Davidson. I spent 22 years doing product development. I understand what you all go through. I've been through every aspect of product development, from working with designers and engineers and the testing group, working with styling department and marketing, last minute changes, working with the plants, trying to get products to launch. I've been there, done it all. I understand what you go through. You've got a hard job. I think we've got some great products here that can really help to get you products to the market faster and better. We've got great development partners. Dassault Systems, ANSYS, MSC, they've been partners with us from the very beginning. They see the value in our product and they want us to get our product to their customers. CE-Tron is our 3D visualization supplier, and they provide us the tools to let us read your databases and visualize all of your models. So we've got a great company and a great platform here, and let's get right to it. Really, this is kind of the elevator speech for True Load. Only with True Load can you use FEA and test to understand all of your product loading. We're trying to help you understand the loads happening to your products so you can do the proper analysis you need to do. This is a snapshot of our clients from our website. This actually is kind of old, but these the clients here that are highlighted in green, these are all companies who have either are users of our TrueLoad software or have worked with us on consulting projects to understand the loading on their products. So they see the value in being able to use TrueLoad to understand the real world loading on their products. So the products from Wolfstar Technologies are TrueLoad. This is our flagship product. It turns components into load transducers. What we'll do is we'll take your FEA model, we'll look at unit load cases on the FEA model and the strain responses there. We'll extract a correlation matrix that relates strain response to loads at certain locations. You'll go instrument up your part with strain gauges and measure the strains, and then we'll take those measured strains, multiply them by that correlation matrix to back calculate the loads. We're basically making a load transducer out of your part. We're making an n degree of freedom load transducer out of your part. Our second product here is a product we call TrueQSE. QSE stands for quasi-static events. And this basically allows you to linearly superimpose results via user-defined functions. And that's great on its own. But what happens with TrueLoad, we're gonna basically get time histories of loading from test that map back to individual result sets in the FEA model, and then TrueQSE becomes a tool that you can post-process the model. You can create XY plots anywhere on any degree of freedom on the model that you'd like. You can create full field operating deflection shapes. And it's so important for understanding the results of your load calculations. We bundle TrueQSE in with TrueLoad automatically. So when you buy TrueLoad, you get TrueQSE automatically. And the third product we've got is TrueLDE. We're very excited about this. We're relaunching this product this year. And this is basically a post-processor for linear dynamic solutions. So basically it focuses on any of the types of solves you can do in linear dynamics: time domain, frequency domain, PSD domain. And the gap that we're filling here is that most of the post-processors out there aren't really tuned for these types of post-processing. And with the LDE tool, you can very quickly and easily post-process your models in a very efficient fashion. And the extra added benefit that you get is that we can, when you set up your models for TrueLDE, your solutions for your linear dynamic events ends up being close to 90% faster. So we end up giving you a supercomputer for your linear dynamic solves when you set up a model for LDE. So these are our great tools. We're really concerned about getting the loads right and make sure the loads are representing what's going on in your structures properly. And since we know loading is such a big important part of doing an FEA-based fatigue solution, we've got interfaces to the major FEA fatigue solutions out there. So if you use our products, we've got interfaces to those fatigue softwares. And so we can make going off to do a durability analysis essentially just a button push. And now that we make it so easy to go off to do a durability analysis, now you can incorporate durability analysis in part of your normal workflow. Whereas typically to set up a durability analysis, you've got to take a half a day out to import data, export data, and you set things up. We make that just one button push and you're ready to go. So if you've got fatigue software for your FEA, we make using that easier. You don't need to use fatigue software with our tools. We've got great tools for letting you understand the response of your structures, but this is an extra added benefit that you get. So the motivation behind TrueLoad is quite simply, what's the load? So if you're a design engineer and you're designing components for this motorcycle, and you've got a responsible for the function and the durability of the motorcycle, but the loading is crazy nonlinear. You can't measure the loads, you can't simulate the loads, but you as the design engineer are responsible for designing functional and durable parts. Well, what do? Well, we recognize that all of the components are basically responding linearly. So we'll put strain gauges on the swing arm, the frame, the crankcase, the handlebars, the fenders, the luggage system, the fuel system. We'll put strain gauges on all of these subsystems and let these subsystems become their own load transducers. And then we can use those loads from those subsystems for redesign and optimization of those components. This is a first to market solution. It's based on a technology called influence coefficients. influence coefficients have been around for probably 50 years, but the problem with influence coefficients historically has been it's been all experimental. So you'd have to guess where to place the strain gauges. You'd go through a lot of work in the lab to set up your correlation matrices. They'd be unstable or unusable, and then you get to the field and you get results that didn't mean anything. We've taken all of that headache out of this, and we've optimized it all using the FEA model and scripting, so we get the optimal strain gauge placement and the optimal correlation matrix. So a little background here. You know, when we're doing simulation, we could have perfect CAD models, we could have perfect meshes, we could have perfect material models, we could have perfect solvers. And oftentimes when we go to throw it in for the solution, we don't actually know what the load is, right? Well, you know, we might make a calculation on the back of a napkin. We might have a departmental standard, but oftentimes when we put a load on the structure, we really don't understand what that load really is. And if you don't know what the load is, then you kind of really don't know what your results are. So, you know, in the US, we've got this term called GIGO. GIGO means garbage in, garbage out, right? So if you don't understand the loads, you don't understand the results. You know, I like to say you might as well just get your crayons out and color the pictures yourself. So the way that we've got to get around this is oftentimes people use load transducers, and load transducers are fine, but the issues with load transducers is that they're expensive, and load transducers can cost, you know, upwards of $10,000. And every time you want to use them, you've got to modify your structure, and you've got to cut away material, insert the load transducer, and now you're measuring something. It may or may not be the actual loads, and worst part is now when you bring it back to the analyst, they're typically working on the as designed part. Now the analyst has got to rework the model to look like your test part in order to use the loads just calculated. So it's not perfect, but this is traditionally what companies try to do when they want to understand loading. Another approach is to use strain gauges. And typically what will happen is the analysts will look at their FEA model, come up with some strain gauge locations. They'll talk to their colleague, come up with some more. They might identify, 30 strain gauge locations. They go to the field, they instrument parts, they collect all the strain data. They look at the strain signals, and they look at the FEA model, and nothing makes any sense. So typically what will happen is you'll concentrate on one or two channels of data at one or two points in time, and you'll work for days, if not weeks, to try to get a load case that correlates just qualitatively, not even quantitatively, just qualitatively. You say, yes, that's my load case I'm going to use for redesign, and then you start your redesign process. And then the next time you get back to the field with your next iteration of your prototypes, you find that you might have the same problem or maybe even new problems, and you repeat the cycle. This is just a typical problem with FEA. I've done this. I'm sure many of you have done this as well too. This is just what happens. So what's wrong? Your company are investing in great analysts, world-class FEA software, you're doing the right things by testing, and you're even investing in tools for doing fatigue analysis. So companies making all of the right investments, but you're not getting the right answers. Well, what's going on? Well, the problem is you've just got too many variables. You got the gauge locations, you got the load cases, and you got the quantity of data. So if you put 30 strain gauges on your part and you went off to the proving ground and you collected some data, you'll have 500,000 data points in that time history. And now you've got 30 channels of strains with 500,000 data points each. At each point in time, you've got a unique loading recipe to recreate those strains. So you've got a task that you just can't complete manually. You can't come up with 500,000 recipes on your own. So you're just kind of left spinning your wheels. So the solution here is TrueLoad. TrueLoad is basically doing what's called in situ load measurement. So in situ load measurement. So we're going to turn complex components into multi-channel load cells. We get to leverage the FEA model to work with the test data. We can work with any FEA. We've got really nice plugins for ANSYS Workbench and Navigus CAE, but at the end of the day, we can work with any FEA to get there. And we'll get optimal placement of strain gauges. And from these optimal placement of strain gauges, we're going to get strain correlated loading. And now that we've got strain correlated loading, we give you tools to run that right into your interface for your FEA-based fatigue. So this is what we're bringing to the table here. So basically, we've got customers in all of these product segments here. So if you're getting loading from the wind, sea, or air, from the customers themselves, or even internal loading, um, we can help you out. So any sort of exterior loading going on your structure, interior loading, we can help you get those loads so you can understand the loading for your product development. So this is a typical V diagram used in product development, and it's very nice. You know, we here on the left-hand side in the virtual world, we'll start off with the voice of the customer, go through product requirements, get into the functional specs, and then we start getting into the design. So we're into the CAD and FEA. So we're doing system, subsystem, and component design. So we're designing our system here all in the virtual world, and when we want to make sure that we're getting it right, then we come up on the physical side and start doing physical tests. So we start at component test, subsystem, system test, up until functional and acceptance test until you finally launch the product, right? And so TrueLoad comes in, and what we're doing is we're leveraging all this really expensive data that you're collecting on the physical test, and we're bringing it back into the virtual world here so that you can drive your simulation models with this very expensive resource that you've gone out and invested in, so that we can make sure that we go through this iteration process fewer and fewer times. Typically, my customers cut these iteration cycles in half and maybe down to just one on a product development workflow. So here's a workflow for TrueLoad. We'll start with an FEA model like normal. These are just normal FEA models. But rather than coming in with a complex set of loads on the model, I'm going to have you decompose the loads into a series of unit load cases. So it might be 1 kilonewton in the X, 1 kilonewton in the Y, 1 kilonewton in the Z. It could be a pressure load, it could be a thermal load, it could be an inertial load. And the way you need to think about these unit load cases is if you could mix them together, can you approximate the operating conditions of the structure? So this is you designing the load sensitivity for your part. You solve those unit load cases, then the TrueLoad pretest software looks at all the strain results for all of those unit load cases, and then gives you, and it will identify the optimal strain gauge placements. And we've got tools in there that allows you to reposition and reorient the gauges, and so that you make it easier for the test guys to lay the gauges. And once you're happy with the gauge placement, we'll extract a correlation matrix that relates strain response to all of the unit loads. So basically, we'll have this correlation matrix that relates strain response to load. We'll store that to disk. We'll take the geometric location information of the gauges, and we'll go into the lab, and we'll instrument up the parts with physical gauges. And now in the lab, all we need to do is strain measurement. So we can measure in the lab, we can measure in the proving grounds, you can measure strains in your customer's hands. We just need time histories of strain data. And then from the strain measurement now, we're going to go into post-test, and post-test is going to take the measured strain data, multiply it by this correlation matrix from pre-test to generate time histories of loading functions. And now these are just loads. You could bring those into your FEA model using normal means, or what I highly recommend is you leverage the true QSE files that get generated automatically. And the true QSE files manage each of the unit load cases along with the corresponding loading functions automatically, and allows you to very quickly and easily reconstruct any response anywhere on the structure, or even generate operating deflection shapes. And now that you've got these strain correlated loads, we can always go off and do a fatigue analysis, because your fatigue solver is going to bring in the material models, the durability calculation engine, and the import from the FEA results, so that your durability calculation tool is bringing all of this really important features in. But the most important feature of doing a durability analysis is to get the loading and duty cycle right. Now that we've got strain correlated loading, now we know that we're getting the right duty cycle here. So we'll actually get meaningful results from our fatigue calculations. So this is really the flowchart for using TrueLoad. It looks a bit complex, but really the first 4 blocks are you turning your part into a load transducer. And then once you've got the loads, you're using those loads to do design and optimization. So typically my customers will go through the first 4 blocks once and go through the bottom flowchart 20, 30 times as they optimize their part. Okay, so this is all based on linear systems and loads. So linear system is where loads are proportional displacements, displacements are proportional strains, strains are proportional loads. It's a linear system. Now we realize everything in life is nonlinear. Okay, we get it. We know things are nonlinear. Everything is nonlinear. But we're turning your part into a load transducer. So we're going to target the nominal regimes on the part. We're going to stay away from welds. We're going to stay away from bolted joints. We're going to stay away from areas of contact. We're going to be in nice nominal areas on the part where the strain response is remaining linear and proportional to the exterior loading. The loading can be as nonlinear as anything. The loading can be sinusoidal, ramp loading, impact loading. That's all okay. We just need that strain response to remain proportional to that exterior loading. So let's take this diagram here and turn it into a couple of equations. So the right-hand side of the triangle, well, that's F equals Kx. So that's Hooke's law, the fundamental law of mechanical engineering. So if your structure is obeying Hooke's law on bulk, then the left-hand side of the triangle has got to apply, which is strain times correlation matrix is equal load. And what we're going to do is we're going to calculate loads as being strains from test times a correlation matrix from FEA. So I talked about the science of influence coefficients earlier. This is the governing equation for science of influence coefficients. So if you look this up in papers, you'll find this equation all over those papers. So let's dig into this a little bit further here. So here we've got strain times a correlation matrix is equal to load. So in this example, I've got 3 unit loads on my model, and I've got 4 uniaxial strain gauges laid on my part, okay? So each column of my strain matrix represents a uniaxial strain gauge. So let's go through this row by row and we'll see how this math works out here. So here I'm going to turn on load case number 1 and turn off load cases 2 and 3. And now I'll record the strain response off the FEA model at these 4 locations. So we'll write those 4 strains down and we'll go to the next load case. So here's load case number 2, turn off load cases 1 and 3. And now at these same 4 gauges, I record the strains. But now these strains are different because load case 2 is different than load case 1. So we're essentially getting the strain signature for each load case. Then we go on to load case number 3. So we turn on load case number 3, turn off load cases 1 and 2, and we get load case number 3's unique strain signature. So now we've got 3 unique strain signatures, 3 unique load cases. This is a well-behaved linear set of equations. We can solve this, okay? This is great. So let's talk about these unit loads a little bit here. These unit loads could be anything. These could be forces, these could be moments, they could be unit displacements, they could be temperatures, they could be pressures, they could be inertia loads, they could even be mode shapes. So if you laid strain gauges based on mode shapes, TrueLoad will directly calculate the modal participation factors for those mode shapes. So that's pretty fantastic. But we can take that a step further. Let's say we had a cover on a structure and that cover was bolted down on its 4 corners. We solved the cover for its mode shapes. And where it's bolted down at those 4 corners, we put unit displacements X, Y, and Z on the 4 bolt locations. And we laid strain gauges based on all of that. What TrueLoad will be doing is essentially called a Craig-Bampton analysis. It would be doing the flexible body response based on the mode shapes, and it would be doing the ground interactions based on the unit displacements. So we get a complete characterization of the dynamic environment from just a handful of strain gauges. This is very, very powerful stuff. Okay, so now we've got this nice equation, strain times C equals F, and the only thing I haven't talked about is C. So how do we find C? So if we take a look at this F matrix, and if we call turning a load on a 1 and turning a load off a 0, that F matrix becomes identity matrix. And then we can just do a pseudo inverse. So we have strain times C equals I, pre-multiply by strain transpose, pre-multiply by strain transpose, strain inverse, and you get C is equal to strain transpose, strain inverse, strain transpose. And that's what we pull out of the FEA model. So this is great. Now we've got this great equation for C, and then we've got millions of places to lay strain gauges. So how do we know where the best places to lay strain gauges are? Well, we recognize that we've got this little inverse here in our correlation matrix. Inverses can be very poorly behaved, and that's not what we want. We want the best behaved inverse. So we recognize that the definition of an inverse is the cofactor of the matrix divided by the determinant. So the thing in the bottom of the determinant, we don't want that to be 0. We want that to be maximum. So our objective function is to maximize the determinant of strain transpose strain, and we do that search with this Galil-Kiefer d-optimal search algorithm. It's a very efficient sequential exchange operation for getting to the optimal strain gauge placement. Okay, I'm going to go through the workflow one more time with a little bit of more graphics here. This will explain things a little bit better. This guy's working on a headlamp from a motorcycle. My background there. And this analyst is saying, Jesus, headlamp's attached to the handlebars. Is attached to the front, which is connected to the front suspension. Is getting input from the engine and frame vibrations. He's going to treat this as a base excitation problem. So he's going to restrain it to ground at the bolts and put 10 Gs X, 10 Gs Y, and 10 Gs Z. And he says that I can basically simulate any sort of base excitation with these three accelerations. And then he solves the model, goes into pretest. Pretest loads up his 3-unit load cases automatically. And then he selects a subset of the model for laying strain gauges. So he's going to pick elements up here in the bucket. And on the legs, he's going to stay away from boundary conditions. And he's going to stay away from the RBEs. He wants to be nice nominal areas on his FEA model. Then he tells TrueLoad he wants 6 gauges, and it draws up his strain gauges on the screen. So you can see the strain gauges are represented as these lines, showing you the position and orientation of each strain gauge on the structure. And once you're happy with that gauge placement, then you go off and you measure the strains from the actual physical part. And now the whole idea is that you want to take these measured strains now and turn them into measured loads, and we're going to do that in post-test. So in post-test, we bring in the TrueLoad pretest file, we bring in the strain data file, and we push this button to calculate loads. It's kind of that simple. There's other buttons here to, plot data, to map channels, but really at the end of the day, we're bringing in the correlation matrix from pretest, bringing in the strain data from test, and pushing the button to calculate loads. And when we do that, then TrueLoad is going to take the measured strain data, multiply it by the correlation matrix to generate the loads. And now that we've got the loads, TrueLoads goes back into the FEA model and pulls out simulated strains at the gauges and shows you measured strain versus simulated strain at each and every one of the gauges, so you can make sure that your loads you're putting in your FEA model is actually reproducing the strains that you measured in the field. Once you're happy with that, you can then go in and use the true QSE files that are generated. So these true QSE files here, we've got our 3-unit load cases now, and then the 3 loading functions that came from post-test that were just calculated from post-test and to simulate the environment. And then we can go and probe any node and element we want for any response we want, or we can generate full field operating deflection shapes. And now this is great. We get to see what our part was doing. This is kind of a rear view mirror look. We get to see what's going on with the part. But now the whole thing is that we want to use this for redesign. We want to redesign this part. So all we have to do is go back into the FEA model and we can remesh the part. So here I made some design changes here, put some holes in this thing, thicken things up. And the only requirement I'm going to put on you now is that you have to solve it with the same unit load cases you started off with. So these are very simple solve, just 3-unit load cases. So you solve these 3-unit load cases. And now that once you do that, then all you have to do is come back to QSE and you swap out the FEA database, and then all the results will be re-superimposed via these loading functions. And then you can generate a new set of full field results based on your design changes. And now if you want to look at what's going on side by side, you can always look at them at your results side by side here. Okay. So this is a super powerful way for understanding your loading and understanding your design changes here. And I know many of you are ANSYS users, so I just wanted to show you our nice little workbench schematic for ANSYS. So this is a typical workbench flow. So here we've got the static structural element on the workbench here, and then we just come in and we drag in the pretest component and hook that up to our solution. And this is where we're going to define our strain gauge placement. So we go through the work here to define where the strain gauges are. Once we're happy with the strain gauges, we will go off and we'll measure strains on the physical part. And then so in this case, we've done 3 tests here, and then we just attach a post-test component to our pre-test and bring in the strain data to these 3 post-test components. And here we're going to calculate the loads from the measured strain. And now that we've done that, then we can hook up our true QSE components to our loads from post-test, so we can go in and query the model and generate operating deflection shapes. Now, let's say we wanted to do a durability analysis. So we could say, you know what, I want to have three repeats of the first event, 5 repeats of the second, and 30 repeats of the third. Well, we can bring that into our duty cycle manager here, and we can make up that recipe in the duty cycle manager, and then it will just output then those that FEA fatigue solver information to our fatigue solver and push that out, and then you can run your fatigue analysis. So it's a really nice workflow that we've got inside of the workbench. And even if you're not using workbench, the steps are still the same if you're working in the native environment. The nice thing about the workbench interface is that all of the TrueLoad files are stored inside of the project folder. And so it's kind of a nice bit of housekeeping too, that everything that you need is stored within your workbench project. Okay, getting to some customer examples here. So this is our first one from Honda. This is from the Honda powertrain department, and they had some issues on these oil passageways on their engines here. And this is a very complex piece of structure here. It's connecting a couple of components together on the engine. They've got thermal, they've got pressure, they've got mechanical interfaces going on here, and they were having some fatigue cracking going on, and they needed to have a way to figure out what was causing these issues. So they were able to very easily go in and use TrueLoad and place strain gauges on this tube using TrueLoad to go in and back calculate the loading environment. And you can see here is just one of their correlation plots of plotting measured strain versus simulated strain and getting excellent correlation on this part. And this gave them the tools then to go in and do a design exploration and actually fix this component inside of a week. This was extremely quick turnaround for them for this very complex problem. This is also another complex problem here. Aaron's is a great customer of ours. They create these zero turning radius lawnmowers, very high-end lawnmowers, and they've got these engine decks. So the engine and transmission sits on this engine deck, and this all sits underneath the seat here. And this structure was working fine for them, but their transmission supplier needed to provide airflow so that the transmission could be cooled off properly. So they called us to see if we could help them do some design changes. So working with the engineers there, we decided to treat the structure as a basic citation problem, because basically this whole tractor is bouncing across their proving grounds, and the engine and transmission are just sitting up here attached to the deck. So we modeled the engine transmission as a lump mass, tied that into the deck, and we put 10 Gs, X, Y, and Z as our unit load cases. And then TrueLoad said to place 8 strain gauges on the deck. So you can kind of see where the 8 strain gauges are here on this deck here. And we place those 8 strain gauges there. And now you can see some of our results. So on the top left here, this plot here is showing all 8 strain gauges that are going across the proving grounds. We use those strain gauges, multiplying by our correlation matrix to generate the loads. And then once we've got the loads, we go into the FEA model and pull out the simulated strains. So actually this plot here has got green curves here are measured strain and blue curves are simulated strain. They're line on line. And down below here, we've got a cross plot of measured strain versus simulated strain for all 8 strain gauges. Look at this. This is nearly perfect strain correlation. And once we've got that, then we can generate this nice operating deflection shape. And now that we've got that, we could do some design exploration. Now, the great thing about this project is that Aaron's has got a very mature engineering organization. They had design guides for these engine decks. So that one of their engineers went in and just did their first attempt at getting this right. And so they had their first iteration of the design and they had it going, and they actually had it on their shaker test. And they were so proud of this, they wanted us to see it. And we went down to look at the part on the shaker test. We went down to the lab, and the part had failed on the shaker test in 1200 hours, I believe. It had failed, and it's supposed to go 10,000. And I said, perfect, give us that FEA model. So here's their design, and you can see the stress and strains that they're getting from this loading that we calculated. And working with the design engineers, we came up with a different pattern. So they basically came up with two larger holes, and we had a double layer of sheet metal here riveted together. And while this worked fantastically, the manufacturing guys hated it. So we had to go down to one layer of sheet metal. And so we had then iterated on thicknesses of sheet metal. And so by the end of the week, we had the design. The next slide, I'm going to show you durability results here on this. Okay. So here we've got here this curve here on the top. This is their material curve, and basically this is showing 10,000 hours of what we want to see. The yellow is 10,000, so we want to see yellow, green, and blue on these plots. So their baseline was fine. There's some red here because of my RBEs, but really their baseline is just fine. And then once we run the true load loads into their first redesign, uh, the fatigue solver was saying this should fail in 1,000 hours, and it actually failed in 1,200 in the lab. So this was perfect correlation with the lab. And having that additional confidence, then we ran that fatigue calculation through on all the designs. And by the end of the week, we had a design that actually had the airflow they needed and actually improved durability than what they started off with. So this is what you can do if you really understand your loads. If you talk to the engineers there, they said, if we had done this project without true load, every time we get a prototype, it costs us $30,000. It takes us 6 weeks to procure. We did 5 iterations, so that would have been $150,000 or 30 weeks. And with true load, we did it all in 8 days. And if you amortize the cost of things, we were under $1,000. So this is the order of magnitude of savings that you can get. And our customers see this all the time. Here's another application of a bulldozer. So this bulldozer here, when I came and talked to this company, they had just launched this bulldozer, and I had their analysis team and their test team in the conference with us, and the managers were looking at me, and they're saying that the proving grounds guys thought the lab guys didn't know what they were doing. The lab guys thought the analysis guys didn't know what they're doing. So each department didn't trust the other department because nobody was getting anything to correlate or match. And they just looked at me and said, Tim, we don't care if this works. If this just gets these guys to talk to each other, we'll call it a win. So working with those engineers, we basically set up XYZ unit loads in the front of the blade. We have a hydraulic cylinder here we had to actuate, so we actuated that, and there's a mechanism on the back we had to actuate. So we had 5 unit loads. We laid 13 strain gauges on this. So we had gauges laid on the arms and on the back of the blade. And you can see on the top right here, the green curves are our measured strains of that from those 13 gauges, and then we use those measured strains then to back calculate the simulated strains, which are the blue curves here. And when they saw this, they thought this was fantastic. They've never been able to get a correlation like that before. But they said, Tim, our real issue were these forgings here on here. They had welds on these forgings, and they had all their development issues were around these welds. And so they laid extra gauges, like this gauge number 19, right up against one of the welds. And so I've got gauge number 19 plotted in green here. And then we go into true QSE and we pull out the simulated strains coming in from the FEA model in that regime. And you can see how well we're correlating to that, okay? So this just goes to show you that if you get the overall flexibility of the structure right and the loading on the overall structure right, the hot spots come along for the ride, okay? All right. This getting down to the last example here. This is a Baja car. We kind of started things off again. So at Wolfstar, we hire graduate students from the University of Wisconsin to come work for us. And it just so happens one year that I hired a graduate student, he happened to be the captain of the Baja car team. And he says, hey, Tim, we want to use your software to understand the loading on our suspension arm so we can optimize it. So we basically set up an FEA model of XYZ loads at the shock, at the wheel, at the stabilizer links. And then this is what all the unit load cases from those unit load solves look like. And then the true load software said, hey, place gauges here on the arm and up here on this forging. You see, most of the gauges end up being on the forging because that's where most of the loads are. We're basically laying strain gauges along the load paths. So So we got these strain gauges laid on all these load paths here from true load, and then we go off and they instrumented everything up. So this was a graduate student and 2 undergraduates. Okay, these guys had never really done any FEA before, so I coached them on how to set up the FEA model. I mean, they had FEA in school, but not on a real part. So I coached them on how to set up the FEA model, and they had never touched a strain gauge. They had never done any data acquisition. So over the summer, with some coaching from me and some other folks, they basically figured out how to do strain gauging and how to do data acquisition, and they wired up this Baja car and got it all going, and they did the true load modeling, and they even went off and they built jumps. And so here's a jump that they built, and we set up the parking structure at the university as a proving ground. So we're collecting data going over this jump here, and then we did um, max brakes and hard turns in the parking structure as well too, and we're collecting data. So this next slide here is showing some strain data that we collected off this jump. And so what you see on the top left here, the green curves are the measured strains from the jump here. So we take the green curves are the measured strains. We take these measured strains, multiply them by our correlation matrix to produce the time histories of loading for our 11-unit load cases on the structure. Now that we've got the loads, we go back into the FEA model and we pull out simulated strains at the FEA model. So the blue curves here are simulated strains from the FEA model. And then we do a cross plot of the measured strains versus simulated strains. And you see how well we're getting correlation here. This is just excellent correlation. I would challenge any automotive company to show me a correlation plot this good, except for Honda, which can do it, uh, for being able to use their measured strain data off their proving grounds and get that to correlate with any of their models. This is a fantastic correlation. And these are just 3 college kids who really have never done anything before, and they did this all in 6 weeks. So now that they've got this and this operating deflection shape, their real goal was to redesign this part. So they set up a little duty cycle here. We said, okay, a typical race course might be 30 hard brakes, 40 hard turns, and 20 jumps. So that's 5.6 hours of time for one duty cycle of their race car environment, of the racing environment. And so when we ran that through the fatigue software says, well, they could do that 278,000 times. So 278,000 times 5 hours, that's a lot of time. They don't need to be that robustly designed. So they went through a redesign process to thin up the tubes. And so they basically were able to thin up all the tubes except for this diagonal tube. And they were able to take 25% of the weight out of the structure just by going in through doing some very simple redesigns here. And to have a high confidence, and they still have got 12,000 repeats. They've still got more structure than they need. And part of what I charge these guys for doing this project with them is that they had to write me an SAE paper, and so this is published in the SAE World Congress, and so this is a peer-reviewed paper that they published for me. Okay, so that gets us through TrueLoad. I'm going to just have a few slides here on True LDE. This is a relaunch of a tool that we've had, and it's a really super powerful tool. So I just want to show you real quickly what we're doing here. So a traditional FEA approach for linear dynamics is that it really creates large storage requirements for all your field data you're collecting. And some FEA, you need to know the nodes and elements here to generate XY data output requests before you do the solve. And then solution times can be slow, largely because of these storage requirements. And then every time you want to generate a new XY plot, you often have to resubmit your deck to basically do a new output request at new locations. And the modal mass participation is not always obvious when you do these solves, and the preload's not considered in your linear transient results. And I think most people don't realize that, but when you do a linear transient analysis, the residual effects from the preload is not superimposed on your results. It does affect the mode shapes, but it is not part of your stress and strain solution. And I think that's a huge surprise to most analysts. So it's just not intuitive, and it's really kind of batch mode oriented. So this is the problem I was solving with LDE. So the basic concept is that LDE, on the modes, we're going to not only store the mode shapes, but we're also going to store other information like stress, strain, reaction forces, those things on the modal solve, on the eigensolve here. And then when you're doing your linear dynamics solution, we're only going to store the modal participation functions for that linear dynamic solution. So this is just a very small amount of XY data that we're storing for the modal scale factors for each of the mode shapes. And then the LDE tool then is going to, on the fly, do linear superposition to regenerate any response anywhere on the structure from on the nodes and elements, operating deflection shapes, or even pushing it off to your FEA-based fatigue tool. So the great features with LDE, you get to include preload. There's no field results stored on the event set, only the modal participation factors. We support time domain, frequency domain, and PSD domain. You have interface to the durability software, all in the time domain. So even if you're doing in a frequency or PSD domain solve, when we push your results off to a durability software, we're going to push it into the time domain, so it's actually the correct solution. Oftentimes your durability tools have very specialized cases that make these things work, but they don't work in the generalized cases. So when we push it to the time domain, we're able to make it work for any solution, okay? And we give you ready to run decks for your durability software. And what's really great is that we can convert your results between time, frequency, and PSD domains. So you could have done a frequency domain solve and you want to look at the time domain, we can flip a switch and we can give you those results in the time domain very easily. And so this has got a familiar behavior. The interface looks very similar to true QSE. So if you're used to using true QSE, it'll be just a natural to pick up true LDE. Here's a benchmark we've done. Here we had a file from one of the major big three automotive companies, and their original deck here, it took 14 minutes to solve in the solver. And when we prepped the output requests to get it ready for LDE, this 14-minute solve went down to 0.62 minutes, 95% faster. And our storage requirements went from 13 gigabytes to 35 megabytes, 99% smaller. These are obviously related, but this is the speed improvements you get. So we're giving you a supercomputer for your linear dynamic solves too. This is what the interface looks like. It's really a super interface, and there's lots and lots of tools here. And I'd love to just spend a separate session to talk only about LDE, but it's really cool tool. And for our current customers, we're making LDE available to them for free through June 1st, okay, so that people could give it a try. And so thank you. That gets us to the end of our presentation. So thank you for hanging on. We've got so many great features that we didn't even touch upon here, from tracking your loads in your animations, to going between time and frequency domains, for looking at gauges of interest and hotspots. We've got design of experiments capabilities, and we've got the ability to export your gauge information into STL files. We've got some really amazing things here. I'd love to spend time to do more of a deep dive with any of you. So please work with the folks at Kionis, and we can work on doing some more one-on-one discussions to do a more deep dive into this. Okay, I think I'm ready for some questions if we've got some time. Let's see if there's anything out there.
Yeah, thank you, Tim, for this great presentation. Very clear as usual. And I think that I hope that everybody enjoy it, because provide a lot of information. Please, everybody, notice the trial date if you want to, because I think it's a great opportunity if you have some needs. If you have some question, you may enter them in the chat also, such that such before for the last time. Just some things to finish and to make some announcements before we answer the question. I will just take back the presentation some minutes.
Okay.
Yeah, uh, sorry, we don't see anything. Up,
It's just blue
yeah,
out there. There we go.
it's better there.
Yes.
So, as we said, Keonis is also the partner and the reseller of True Road, and that's the reason why we are very delighted to invite you, Tim, to present your solution. Just to remember everyone that Keonis is here to advise, train, help, and support you in your simulation challenges. And I think TrueLoad may be quite high help. Of course, the large scale is with Tim Hunter in his team, but we are here to put you into contact if required. For next webinar, which will take place the 27th of May, retroconception of your pieces with a 3D experience. So we will see with some sort of reverse engineering. I think it could be very interesting also. So let's see it in some weeks.
Okay.
Yeah. Any question, Tim?
Well, so I know in the past I've gotten some questions. For example, people ask about rosette gauges, and so
Yeah.
do we need to use rosette gauges? And with TrueLoad, TrueLoad is designed to work with uniaxial gauges. So basically, we're working with the most inexpensive strain gauges you can get. And sometimes people have rosette data that they've got already that they want to use in TrueLoad. So we can basically force a rosette gauge by basically stacking 3 strain gauges on top of each other to make them look like a rosette. But that's, we don't require rosettes, but sometimes people bring us rosettes to work with, and we can work with them just fine. But by default, we're working with uniaxial gauges. So, um, uh,
Would you like to take back the screen in order to share some things, or it's all right for
I
you?
don't really have anything to share, to tell the truth. I mean, I'm just I could just talk to some questions.
Yeah, good.
Yeah.
Okay.
So there's a question here. Is there a maximum number of loads slash gauges? Uh, so TrueLoad is doesn't have any design limitations for the number of strain gauges or loads or mesh size for that matter. It's basically your computer hardware limitation. Okay, so I've done projects with hundreds of strain gauges. Okay, and and hundreds of load cases. It's doable. Um, just the bigger things get, sometimes things run a little slower. But the real thing that drives the solution speed for TrueLoad is actually the size of the FEA model, because the TrueLoad solution needs to go into the FEA model and query the strain tensors out of the FEA model. And so the larger the FEA model is, the slower the query times are against the FEA model. But the matrices we're working with in TrueLoad are relatively small in our computer technology these days. You know, if you've got 10 loads and 20 strain gauges laid on a structure, your strain your matrices are going to be 10 by 20. Okay, so it's still a very small matrix. Okay, but the real overhead is working with these large databases. So um, there are some things we can do when we set up the database to be a little bit more efficient for storing results, but really it's the size of the databases is a real speed impactor for TrueLoad. But there's no limitation for the numbers of loads or gauges, as many as you can think of. And on top of, the real limitation for gauges with my customers, it's always their test department. It's how many channels of strain measurement can they do. So that's always the limitation. So that's really the limitation that you're running into. So is usually is how many channels of strain data can you measure. So all right.
Pretty well.
Okay.
Uh, so I hope that everybody has noticed all the opportunity, all the advantage that TrueLoad can bring to Abacus and FESafe for your daily life if you are of course, confronted with such challenges. So, has everyone any other question? Or is that all right? Okay, seems it's all right. Thank you again, Tim, for your great presentation. It's a
Great.
pleasure to have you with us today.
Well, super. Thank you very much. And please reach out, and I'd be happy to entertain any more questions after the fact. Thank you very much.
With pleasure. May the force be with everybody, and have a very nice day.
Okay. Bye bye.
Goodbye.